All right, I think we should start now. We have given enough time for everyone to join. So myself, I'm Abdullah. I teach physics for the past 5 or 6 years. Basically done my own education in physics. So I have done one master's in physics and then an MPhil in physics as well. And it's just a passion. I am doing it out of passion. I really love physics, as you may be able to tell. So let's just move on with the topic. So we have waves. So waves is you can say that how like energy is transferred from one place to the other for some of the particles that obey physics. Sorry, I mean waves. So what happens in waves is that the particles themselves, they just vibrate at their own position. It's only the energy that is transferred to the adjacent particles. Like for example, if you disturb water, where the disturbance is, it the wave just starts from that point, and the particles they just vibrate on their one of the axes, and the wave just travels perpendicular to that, which means the energy travels perpendicular to that, and it causes the like the disturbance in the adjacent particles as well. So a wave transfers energy away from its source. That is what I explained. So a progressive wave, which is moving, carries energy from one place to another without transferring any material, because the material it just vibrates at its own position. And after all the energy has been transferred or the source is removed, you'll see that particles just come to rest at the same position. They don't move at all. They just come back to that mean position that they were before. So there are a lot of examples of waves. A lot of things obey waves. It could be sound that obey waves. All of the electromagnetic radiation that actually moves or transfers energy in form of waves. So let's just go into the how to quantify a wave. So what are the different aspects of wave using which we can quantify it? So if you have to show a wave on a graph, there are two ways. One is displacement versus distance graph, that you can take an example of water waves. So you can see that if you move away from the source, that is what this distance shows. And this displacement is basically the vibration of the particle, the to and fro motion from the mean position at the same point. So that's that. If you want to see the other type of graph that you can have, that is displacement versus time graph. So basically it's taken just at a single point. Let's say, again taking the example of water, so if you just pick up a point wherever you have the wave, and you can see the particles move up and down, that is shown by this type of graph. And you can see that as time goes on, it goes up, then it comes back to the mean position, the vibration, and then goes to the other extreme. So that is the two ways of showing waves using graphs. The quantities that we use to describe a wave mathematically, those are displacement, amplitude, wavelength, period, frequency, phase, and phase difference. Displacement is actually how much it has, so the particles, how much they have moved from their mean position, which is the rest position. So you can see from here that the y-axis shows the displacement. So it shows that, for example, the particles that are here, they basically have moved a little bit up from the mean position. And similarly, the particles, when they reach the extreme position on one end, the distance at that time or the displacement at that time is called the amplitude. So that's shown by this. So obviously this is amplitude. Any other point is not an amplitude. And then on the other extreme, that is also an amplitude. So that's what amplitude is. And obviously this is also displacement, but a specific name is given to the displacement, which is to the extreme position, and it's called amplitude. A lot of times in the exam, they, instead of using displacement, they use amplitude. But whenever they have not used the word amplitude, and you know it is not the amplitude, it's not the extreme position, you will always use the word displacement at that point. Now the wavelength is a complete cycle of the particles. So for example, if you start from this point, you know it's at the mean position right now, then it goes to the uh, first extreme position. Then it comes back to that mean position, but this mean position, this is a bit different because after this, the wave starts to travel in the other extreme position, and then it comes back again to the mean position, so or the undisturbed position. So starting from this point, coming back to the same point, this distance that you have covered, that is one wavelength. So obviously it is measured in meters because it's a distance. Then period is the time. So now obviously if you have to directly measure the wavelength, you can do so in a displacement versus distance graph, but obviously you can't measure it in measure the period using the displacement versus distance graph because you don't have the information about how much time it has taken for the wave to go up, then come down, and then go to the other extreme position. So you can directly measure the period using displacement versus time graph. Period is how much time the wave takes to go from the undisturbed position to one of the extremes, which is the amplitude, then come back to the undisturbed position, then go to the other extreme, and then again come back to the same point, like one wavelength that was covered in displacement versus distance graph. So that whole period or that whole time is known as period. Similarly, frequency. Frequency is how much part of that wavelength has passed each second. It's measured in hertz, which is per second, and it's basically the inverse of period. So this is the first formula that we encounter, which is frequency is equal to 1 over period. So and the unit that is given to frequency is hertz, which is essentially just per second. So that's that. Phase is the measurement of the position of a certain point along the wave cycle. So, for example, so phase is always measured in the units of angle, and the units of angle are degrees and radians. But most of the time, because we have to use it in the formulas, so we always prefer radians to do that because it's the part of system international unit. So a measurement of the position of a certain point along the wave cycle. So this point is, you can say that this is 0 degrees or 0 radians. Then the first extreme position, that would be 90 degrees because the whole cycle is going to be 360 degrees. So the first extreme position is 90 degrees, and you can also say in radians it's pi by 2. Similarly, this position is 180 degrees, and you can say this is pi. Similar to that, this is 270 degrees, and this is 360 degrees. So that's phase. Phase difference comes into play when you have more than one wave. So you both of them, let's say, are traveling in the same direction. So maybe one is ahead of the other. So just to measure what is the difference, like how much one is ahead of the other, you just measure the phase difference, which is you measure the phase for one of them, then measure the phase for the other one, and then just take the difference. So that is phase difference. Normally we do it in radians as well. So that's that. This is the first formula that we encounter. That so frequency is like the inverse of period. So maybe that will come handy when we solve the past paper questions. Uh, so the formula of the frequency. So I'm not sure if you would need to like derive it. So basically they are just inverse of each other. So you know what is period? So period is when one whole cycle of a wave has passed. And frequency is how much of it has passed in a second. So that's why they are like you take the inverse of one and you get the other value. So that's just that. So it's really basic, and I don't think there would be any derivation for this. So that's that. But coming to the wave equation, so that is the second equation that we encounter, but that is derived from just the formula for speed, which is distance over time. So we now know that for a whole wave to have passed, that is the time that it takes is the total period. So you can replace time by t, the capital T, which is period, and the distance that would have passed would be one wavelength, as I said. So this is wavelength over period, and as we know that period and frequency are like the inverse of each other, so you can replace period by frequency, and then we come to this formula, which is V equals F lambda. So again, this formula is just derived from like the simplest formula for speed, and now you know how it is done. You won't need it, but just for the understanding, it's V equals F lambda, and it is derived from the simple formula of speed. All right. And there you just explain the oscilloscope, how it works. So you can actually like see the waves because you have actually provided it with an input of maybe sound wave, which is converted into voltage. And then you see the wave like the, so now this is displacement versus time graph that you see in an oscilloscope. And the x-axis is time. You can control what a small block represents. Does it represent a second? Does it represent less than a second? So you basically can control it using a dial here. And the other dial is to control the y-axis, which is the displacement, because it could be that you have a wave that has a displacement of, let's say, a meter, and these small boxes, they just represent maybe 1 millimeter. So you can use this dial to actually change the scale of the graph. So that's as simple as that. Uh, yeah. You can find wave frequency. Obviously, you can find the wave frequency using an oscilloscope, because as I said, that period is the inverse of frequency. And since this is a displacement versus time graph, if you look at the wave that is shown here, you can just count the distance between one crust. Now, these extreme positions are called crust, and the undisturbed position is called trough. So you can basically calculate the time from starting from one crust to the other. So you can just calculate that and just take the inverse of that, and you'll get the frequency if something like that comes up in the exam. All right. So pretty basic so far. Just the formula for frequency and period, and also V equals F lambda. As I said, it is derived from uh, the simple formula of speed. And I already told you you can have two types of graphs: displacement versus distance and displacement versus time. As you can see here, you can get directly the wavelength from displacement versus distance graph. You can just calculate how much distance is starting from the same position, going to the same position again. You can start from the crust, go to the adjacent crust, like in the positive direction, and then you can start from maybe the start and go to basically the same point again. Obviously, it looks like that this is the mean position, and then it comes back to the mean position again here. But if you know how to calculate the gradient, these two positions have different gradient, right? So we know that the whole cycle has not passed. And also, if you try to calculate it using phase, you know that a complete cycle would be 360 degrees or 2 pi. So you start from here, 360 degrees would be completed at this point. So that is a total wavelength that you need to calculate. All right. Yeah, so this is the mean position. Crust is the one of the extreme position, then trough is the other extreme position. Right. So so far it's not that difficult. Then we have intensity. So intensity is another thing that has been quantified. Intensity is just the power that is spread in a unit area. So it could be, like I said, that electromagnetic waves are also waves, as I said in the name as well. So some lasers are like, that they are classed to be very dangerous for humans. So the thing that happens is that their intensity is quite high, and also it could be that their ionization power is high. I don't want to go into the detail of that, but intensity, it's a very important thing, because it tells us how much concentrated the power is in an area, because that tells us how dangerous it is, or how much effect it would have on something, because how much concentrated the power is. So it's a very basic formula. Intensity is just the rate of flow of energy per unit area at right angles to the direction of travel of the waves. It is at right angle to the direction of the waves, because that actually tells us how much power is concentrated at a single point. So intensity is just power over area. Uh, and yeah, as I have explained it already. The other thing that you need to know, it's not in terms of an equation, it's a relation between two things, which is intensity and amplitude. Amplitude from the graph. You can easily measure the amplitude, which is the distance from the undisturbed position to any of the extreme positions. So intensity is directly proportional to the square of amplitude. Now, this has not been written in form of an equation, but you can change it into an equation by taking the ratio here. So let's say you have two intensities and two different amplitudes of two waves, let's say. So you can just make a ratio out of it, like intensity of the first divided by amplitude of the first should be equal to intensity of the second divided by the amplitude of the second. I mean the square of them. Because if you take amplitude on this side, it would be intensity over amplitude squared, which would be a constant value because that's how we get rid of the proportionality sign and get an equation. So you can basically use those ratios. Maybe we'll solve a question that actually tells how you do it. So just remember intensity is the power that is concentrated in a unit area. And the relation between intensity and amplitude is that intensity is directly proportional to the amplitude squared. And amplitude is something that you can directly measure from the graph if the graph is given to you. All right. Now, EM waves, EM waves, part of that is light as well, the visible light, because that is part of that spectrum. So EM waves are the waves that have electric field as well as magnetic field associated to them. Both of them are at 90 degrees to each other, but the energy is traveling in the same direction. So EM waves have some properties in common. All of the EM waves in vacuum, they travel at the speed of 3 times 10 to the power 8. Obviously, it depends what material they are going through because the speed changes as the optical density of the material changes. So when they say the speed is 3 times 10 to the power 8, it is usually in vacuum. And also we take the assumption that it is same in the air as well. So if something is traveling in the air, you just take the same speed, but this speed would be different when it is traveling in, let's say, glass or something that has different optical density. We'll come to that how we know what optical density is of the material because that depends on the refractive index, because the quantifiable thing about the optical density is the refractive index. We come to that. All EM waves like light, X-rays, microwaves, infrared, all of them are transverse waves. I'm not sure if I went through that. Yeah, so transverse wave is when vibration, like water particles, when you disturb water. So vibration is like this, but the wave is traveling in this direction. You can see that the wave is progressing as you disturb water. So so basically, transverse wave is vibration is at right angles to the direction of travel. So you can see this. If you disturb it from here, you'll see that eventually you will see that waves are now starting to arise in other parts of this spring as well. So this is transverse wave. Whereas the biggest example is EM waves, which is visible light, infrared, microwaves, and all the waves like that. Whereas the longitudinal waves, the only example that is uh, discussed here is sound waves. We mostly discuss only transverse wave, but a little bit of longitudinal wave as well. So the biggest example of that is sound waves. The difference between transverse and longitudinal is that longitudinal wave, the vibrations are in the direction of the wave travel. Like if you see the example of the spring, uh, they have caused some disturbance to the spring, and you can see that the compressions and then the when it is uncompressed, which is called rarefaction, the vibration, this is basically the vibration, it also travels in the same direction as the energy is traveling or the wave is traveling. So this is longitudinal wave. So that is the definition of longitudinal wave. And then coming to the EM waves, EM waves are also transverse waves. That's why EM wave, as the name suggests, it's electrical wave and magnetic wave, or electrical field and magnetic field, traveling 90 degrees to each other. Like if one is traveling like this, the other would be traveling like that. And they both of them are still perpendicular to the direction of travel because you can have three directions in space, right? So both of them are at 90 degrees to each other and to the direction of travel as well. So yeah, and this is a spectrum which is separated from each other in terms of wavelength. So obviously, the wavelengths can start from, let's say here starts from, so the one of the extremes of the wavelength. It starts from radio waves. These are the longest EM waves, coming down to the gamma rays, which have like the shortest wavelength that's possible. So 10 to the power minus 6 to 10 to the power minus 10. And in the middle somewhere we have visible light as well. So the light that we can see, all of the other things we can't see, but they are there. So they have different penetrations and uses uh, depending on how much energy that they have. We'll come to those like formulas as well to be able to differentiate between them. But the biggest differentiation between them is the wavelength. They have been separated from each other based on the wavelength. So, as I said, so visible light is somewhere in the middle. If I convert this from meters to nanometers, it's basically starting from 400 and goes up to 700 nanometers. It starts from 350. We are able to start to see violet light starting from around above 350 and goes up to 750 where we see the far red light. But they have just approximated it here so that we can see it in meters. All right. So that's that. Now, this is another phenomena that can be associated to waves, but only to transverse waves. So polarization can be done, but only for transverse waves. You can't polarize sound waves because they are longitudinal. So this is something. So far what we have read everything like wavelength, frequency, or those are associated to all types of waves. But polarization that can only be uh, performed on a transverse wave and not on the longitudinal wave. So a polarized wave which has been subjected to polarization only oscillates in one direction. So there could be that a wave is a jumble of different directions. So it could be that it's a sum of wave moving in a single plane, and then there's another component of the wave that is moving in the other. So it's basically like a jumble of waves. You can basically polarize that, which means that you can make it go into the direction you want. So you cut off all the other waves that are going in different directions. You just have one direction that you can see. So basically, if you see like uh, this example that they have shown here. So it's like a vertical fence, and they are like uh, swirling this rope through it. So now you see here, this can be divided into different components. Maybe one is a perpendicular component, the other one is a horizontal component of wave. When it goes through it the fence basically blocks the uh, the components that are traveling in other direction other than the vertical direction, and the resultant is just a single plane of wave which is vertical, as you can see. So polarization is you make sure whatever however you want the wave to travel through in whichever plane, you can do that, and that would be called as polarization. What you use to polarize, for example, EM waves, is a polarizing filter. So what it does is it blocks all the lights in other planes, or the ones that have different direction components. You just have one single uh, plane of wave that can travel through those polarizing filters. And yeah, that is called polarization of waves, or polarization of EM waves, polarization of light. The same phenomena is used in uh, polarized sunglasses as well. They only let light through a specific angle, or the waves that are in a specific angle go through them. So that's polarizing filter. Now this is also important. You can maybe you have performed this experiment in your college as well. So they have similar polarizing filters, and there's some unpolarized light, which means that it could have components in various directions. So it could be a jumble of waves that are vertical, horizontal, and in the middle as well. So you let it pass through one polarizing filter first, and you can see that has vertical stripes, which means that, as this example, it will only let the waves pass through in like in the vertical plane. And when it passes through that, obviously, if you have the other filter horizontal, no waves would be able to pass through it, because uh, essentially this would block everything because you only had vertical waves passing through the first one, and through the second one you won't see anything passing through because it's horizontal, so it won't let anything pass it. But if the second polarizing filter is at an angle, then you can basically use basic trigonometry. Like if it is an angle theta, you can basically find the vertical component of these stripes and see how much weight the vertical component of that has, and it will let some of the waves pass through it because of that. So if it is horizontal and only vertical waves are coming from the first polarizing filter, nothing will go through the second polarizing filter. But if it is at an angle, let's say they have said that it is at a 45 degrees angle, it will let half of the energy pass through it because if you solve it using trigonometry, you will find that the vertical component can be found using sine theta. You can find that vertical component of the stripes, and you'll see that half of the half of the energy is still going through the second polarizing filter. But obviously, if it is horizontal, nothing will go through it. So it says the same thing here. Just like vectors, you can think of transmission axis of rotating filter as having a vertical and horizontal component. So if it is at an angle, these stripes would have a vertical and horizontal component. The larger the vertical component, which means the larger the angle, because sine theta comes into play if you try to solve it for the vertical component of this. So the larger the vertical component, the more vertically polarized light will pass through the filter. So that is what it is. All right. I hope it's making sense so far. Okay. And obviously the distance between these stripes is also significant. Uh, it should be comparable to what wavelength of light is passing through. So if it is too big for the wavelength, obviously you won't see much of polarization happening. It should be comparable to whatever the wavelength of light you are using to perform this experiment. So just like microwaves. Now microwaves, if you have seen this, microwaves have a longer wavelength. So if you use these small polarizing filters for that, you won't see anything passing through, like any polarized light passing through or any polarized EM waves passing through it. So for that, you can use a metal grill because then it would be like comparable to the size of the wavelength. So you can use a metal grill to basically polarize a microwave. The phenomena would still be the same as these polarizing filters. It's just that the distance between these grills is now comparable to the size of the wavelength. All right. Then they just talk about the same experiment here. I'm just going to move forward. So we have so far studied polarization, and you should know that that only is applicable to transverse waves. You can't polarize sound waves. So polarization is the only thing about waves that is only related to or is only applicable on transverse. Other things that we study like diffraction, reflection, refraction, all of them are applicable on transverse as well as longitudinal waves, right? So what is diffraction? Diffraction is the spread of waves when it goes through some slit or some small space or around the corner. So light, we know that it travels straight, but if the size of the gap or the slit or any spacing or any gap, if it is smaller or comparable, sorry, not smaller, comparable to the size of the length of or the wavelength of that wave, you will see the phenomena of diffraction, which means that it won't go, it will still go straight, but it will kind of spread off to the slit. So waves go round corners and spread out of gaps, provided that the gaps are comparable in size to the wavelength of wave that you are currently studying. So you can basically have a look at this phenomena in a ripple tank. So you basically uh, have a wave generator there, and you can see that these are the waves. If you see from the top, you can see that maybe these lines represent the crust, and you can see the crust from the top as it passes through a very big spacing or a very big slit, you won't see any spread after the slit, because the size of because the wavelength, it is so small compared to the gap between those slits. But as you keep on making the slit size smaller and smaller, now it is coming in like that size frame where it is comparable to the wavelength of the water waves, and then you will see that it's now spreading. And when it is near to the size of the wavelength, you will see the most spread in the wave, as you can see here. But if it becomes even when the slit becomes even smaller than the wavelength, then you won't be able to see any diffraction. You would just see reflection from there. All right. So that is what this says here. Now, diffraction in light using laser light. So you can also see it using laser light. If you know the wavelength of the laser light, you need to keep the slit size comparable to the wavelength of the laser light, and you will see that there is some diffraction in that as well. We'll discuss this in detail when we go to double slit experiment as well. So you get a similar effect around an obstacle as well. So this was slit, and because here it says round corners, it does the same thing. So this can be considered as a corner. So you can see the waves are coming here. Now, this can be considered as a corner. So you can see that waves again start to spread here and from this part as well. So that's why you can see that the shadow, it's not like it goes straight from here. It's basically it becomes like a cone. So maybe if I talk about it in terms of light, maybe a person standing in front of a tree or a little bit away from the tree, maybe he can see behind the tree, provided that the thing he wants to see is very far away from the tree, if that works, or the wavelength matches to whatever the gap is. So basically this is what they're saying. So it can work both ways. It can work through slit, and can also work through gaps or like corners, as you can see here. Now, same effect of diffraction when we come to discussing light waves. Obviously, the size of slit again would be comparable to the wavelength. If the wavelength of a light is roughly similar to the size of the aperture, so this is an aperture, you get a diffraction pattern of light and dark fringes. You see something like this, which would be explained better when we discuss interference, because this actually shows where there is constructive interference and destructive interference. We will come to that. The pattern has a bright central fringe with alternating dark and bright fringes on either side of it. The narrower the slit, the wider the diffraction pattern. But if the slit becomes so narrow that it's below the wavelength of light, then you would not see any diffraction. It will just get reflected back. Now, what is reflection? We'll discuss it more detail in the later topics. So wave can be reflected. I think you're already aware of reflection of light, visible light. You can see yourself in the mirror. That is one example of reflection. So reflection means the wave is bounced back when it hits a boundary. The angle of incidence always equal the angle of reflection. So what you need to know about it, let's just see. This is they are saying it's a barrier. Let's say that this is a mirror. The incoming wave is coming. It's coming from this side. What angle it makes with the normal to that mirror is called incident angle, and the reflected wave, it makes another angle which is called angle of reflection with the normal. Now, in reflection, these two angles are equal to each other. So whenever a wave is reflected from an obstacle or from some thing that's blocking it to go to the other side, you will always find that the angle of incidence is equal to angle of reflection. And yeah, so both of these angles are equal, and these angles are made between like the incoming wave and the normal, and for the reflected wave, it is between the outgoing wave and the normal. The normal is just at 90 degrees to the surface of the mirror. All right. I hope it makes sense. There's nothing else here. You just need to know that these two angles are equal to each other in case of reflection. So reflection can also occur if there's a slit. If the slit size is smaller than the wavelength, then you'll see reflection. or if it's just a mirror or something that the light bounces from, then again it's reflection. Now the other thing is refraction, which is slightly has more information than it has more information than reflection, so it has more formulas as well. So refraction is when light goes from one medium to the other. It does not get reflected, it just travels from one medium to the other. That's called refraction. When we say one medium to the other, they should be have different optical density. When I say optical density, I mean that they have different refractive index. We will come to that what refractive index is. But let's say light travels from air to water. Those are two different mediums. So you will see the phenomena of refraction there. All right. But you can sometimes also see reflections. It's not like all the light which is subjected to that boundary between air and water, all of it will go in the water. Some of it still gets reflected back, and that's why you can see yourself in water as well. So you can see your reflection. But obviously, most of it will be refracted in that case when light travels from one medium to the other. It depends what optical density there is. So the other thing you need to know about refraction, again, we are going to use normal all the time. So normal is just something that is 90 degrees to the boundary, similar to what we saw in reflection as well. So you can see that uh, light makes some angle with the the normal when it is traveling from the air. Let's say it's air outside and this block is water. Let's just assume, makes it easier. So this is the incident angle, and on the other side you have the refracted angle that it makes with the normal. Now what we know is when light travels from an optically less dense material to an optically denser material, uh, the light will get uh, it will move towards the normal, which means that incident angle will be greater than the refracted angle. Similarly, if light had to travel from water outside in the air, now water had more optical density than air, so it will move away from the normal. Now, to explain this better, you should know what I said earlier, that the speed of light was said to be 3 times 10 to the power 8 meter per second in vacuum, and we take the same value for air as well. But as light travels from to like other optical density materials such as water, its speed becomes slower. When it becomes slower, what happens is uh, what happens is that it actually bends. Now to explain it better, let's see if I can find something. Let's see if I can find an image that explains it better. Now, as I said, uh, let's look at this example. So, so let's say, let me see if where it is going through. Yeah. So, as light travels, so let's say these are the wave fronts. So, let's say it travels from air to water. What happens is that this part of the wave, it goes into the water first. Now what happens is it becomes slower to the part of the wave that is outside water. So now if the part that goes inside becomes slower to the part that is outside, there's a turn in the wave. And when there's a turn in the wave, it just turns towards the normal, is what happens. So it travels in. One edge of the wave enters the water first, and its speed slows down as compared to 3 times 10 to the power 8 meter per second, which was in the air. So it does not travel at the same speed, but the part that was outside travels with the same speed. So it kind of bends. And because of that, the angle of refraction is less than the angle of incidence, if that makes sense. You can always so this was just for the understanding, but you can always find that using Snell's law. So Snell's law is that n sine theta. Before going to that, I want to talk about refractive index. So refractive index is something that compares the speed of light in that medium to what it was in vacuum. So as I said, in vacuum, it's the maximum speed of light that it travels with. But outside, if it goes into some other medium, its speed would be slower. So that ratio, speed of that wave in or light in vacuum over speed in that medium actually gives us the value of refractive index. It would be one for uh, it would have a value of 1 for vacuum, and we take the value of 1 for uh, wave traveling in wave traveling in the air as well, because it is very close to 1. Obviously it will be greater for other mediums because v would be smaller compared to the speed of light in vacuum. So it will have so whenever refractive index has a greater value, we say that that medium is optically denser than vacuum. So yeah, so this is the formula for refractive index. It's the material measures how much it slows down light. So basically that is what it is. Snell's law just says that this is it just says that the refractive index times the angle that light makes in that medium over the boundary is always a constant value. So let's see this example. So you have N1, the refractive index of, let's say, air, N2 is the refractive index of water. So N1 sine theta 1 is a constant value. So N1 sine theta and N2 sine theta 2 is also a constant value. So both of them are equal to each other because they are equal to that constant. So N1 sine theta 1 is equal to N2 sine theta 2. So that is another equation that you should remember. So based on this equation, you can solve any question that comes with like which shows any refraction. So n1 sine theta 1 is equal to n2 sine theta 2. So and just remember that, and you can basically prove it from here as well. So from less dense material, if light goes to more optically dense material, the angle of refraction would be less compared to the angle of incidence. So just remember that. And similarly, when light goes from an optically dense material to less dense material, the angle of refraction would be greater than the angle of incidence. You can explain it in the same way as I explained it from the figure, or you can just remember this formula. But this understanding is required to understand what is a critical angle. So now I said that when light travels from an optically dense material to less dense material, the angle of refraction is greater than angle of incident, right? So if light is traveling from water outside in the air, uh, the angle of refraction would be greater than angle of incidence. So if you keep on increasing the angle of incidence, the angle of refraction will keep on increasing. Now, angle of refraction would reach 90 degrees before angle of incidence because angle of refraction is greater than angle of incident, right? So there comes a point where you give the incident wave an angle, and the angle of refraction becomes equal to 90 degrees, which means that no light actually goes beyond the boundary. Now, this angle is called critical angle. You can't have any critical angle when light travels from air to water because light must travel from an optically denser material, which means that from a material which has more refractive index value than the material that it is going in. So any you can't measure a critical angle going from less dense material to more dense material because angle of refraction would be less in that case to the angle of incidence. So this is the phenomena only associated with when light, let's say, travels from water to air. So you keep on increasing the angle of incidence, there comes a point that no light makes it way through the boundary and it just gets refracted on the boundary. This angle is called incident angle. Sorry, this angle is called the critical angle. If you go beyond the critical angle in this case, no light would be able to travel into the air, and all of it will be reflected back. Now, in this case, when the angle becomes greater than the critical angle, uh, now we will follow all the rules that we studied for reflection because no light is going to be subjected to refraction anymore. So whatever angle it makes here would be the same with the normal that the angle of reflection makes in that case. All right. So they have just tried to simplify the same thing. So C is the critical angle. We know that angle of refraction at that point would be 90 degrees. So they have just used the same formula, this one, and they have also this is for a particular case where they have taken air. So that's why we know that the refractive index of air, we just take it as 1. So this is the same equation. They have just like simplified it, but this can be only used when there is a critical angle and the boundary is between a material and the air. So if you don't remember that, no worries, just remember this equation and the understanding of critical angle. I hope this is clear from here. All right. So that is critical angle. We have understood this. Now, what is superposition? Superposition is when two or more waves pass through each other, there comes a point when they are like at the same position. Now, what happens at that point? Whatever is the amplitude of one and the amplitude of the other, it just adds up. So, in the first example, you see both of them are traveling opposite to each other, and there's a point when they reach each other and they are at the same point. Both of them have a crust. So, at that instant, when they are at the same position, the amplitudes of both of them would add up. Let's say the amplitude of this is 1 meter, let's say, uh, which I don't know in what case would be possible, but let's say that it's 1 millimeter, and the amplitude of this is also 1 millimeter. So at the point when they are at the same position, which is called superposition, because both of them are at the same position, that is the phenomena known as superposition. The amplitude would add up. So 1 millimeter plus 1 millimeter, the total amplitude of this one would be 2 millimeter. And similarly, if one has a crust and the other one has a trough, and they meet at the same point, and they have the same value of amplitude, 1 meter for the other one, because it's displacement, it's -1. It's in because it's a vector. So you add them up, 1 - 1, it would be 0. So that's why when they meet, you just don't see any wave at that point. So superposition means one thing on top of another thing. You can use the same idea in reverse. A complex wave can be separated out mathematically into several simple sine waves of various sizes. So if you have just one wave, you can maybe split it into two. Like you can say that, okay, this wave has a 1 millimeter amplitude, but it may be comprised of two small waves having zero point 0.5 millimeter each amplitude. So you can so this is used in mathematics when they have to solve complex problems, but I don't think any of that is going to come in your exams. So you don't need to worry about it. What you need to understand is what superposition is. So when two waves meet each other, they are traveling in the opposite direction and they pass through each other. So what happens is the resultant of those two, that is the phenomena is called superposition. Now, when I said you can add them if trough falls on the trough, if trough falls on the crust, they just they can just cancel each other, provided that their amplitude is the same. If the amplitude of this is 1 millimeter and the amplitude of this is -2 because it's in the other direction and it's displacement -2 millimeter, when they meet together, the resultant would be -1 millimeter. So you will still see a wave at the like a trough at the bottom here. So what is that is happening when you calculate that uh, resultant? That is called interference. Those two waves interfere with each other when they constructively interfere. So there are two types of interference, constructive and destructive. When they constructively interfere with each other, that means that crust is falling on the crust of the other and they are adding up to each other to make a bigger amplitude. So that is constructive interference. Destructive interference is when crust of one falls on the top of the other and they completely cancel each other out because they had the same amplitude. So that is called destructive interference, provided that they have the same amplitude, because otherwise they won't be able to like completely cancel the effect of each other, right? So one is constructive, the other one is destructive. Let's just move forward. Okay, it also says uh, it's not like interference does not happen if they don't have the same amplitude. It still happens, but for you to be able to notice it, because one is some big value and the other one has a small value, obviously there would be interference between the two and one will cancel the effect of the other a little bit, but you will still see some wave, so you won't be able to notice it. If you want to notice it, like see the flat line, you must have those two waves having the same amplitudes. All right. Now we talked about phase before. It's the same thing. You just measure the in terms of angle, measure what the angle is for some. So the complete cycle would be 360 degrees, 2 pi. So if you go half of that, it would be 180. If you go half of that, it would be 90-degree here, or pi by 2. And obviously starting point is just 0. So that is the phase of different points in the wave. All right. Uh, okay. And phase difference is if you had two waves here, and you just, let's say one wave was had a crust at this point, you can measure what's the phase at this point and how much distance you have to, in terms of angle, you have to cover to reach the crust of the other. So that would actually contribute towards what the phase difference is for that. All right. So when we say that two waves have to, like I think we'll see it later as well. So if two waves have to uh, constructively interfere with each other, crust would fall on the crust of the other. In that case, both of them should have zero phase difference, so that one the crust of one can fall on the ground. If they have some if they have some phase difference in them, if they have if they have a phase difference of multiples of 2 pi, 0, 2 pi, 4 pi, which is 0, 360, 720. So in that case, obviously the crust will fall on the crust of the other, and there will be constructive interference. If you want to see destructive interference, the phase difference should be 180 degrees, because 180 degrees just means that it's like this. So the trough of the one of them falls on the crust of the other. So you need an odd multiple of 180 degrees or pi radians in terms of the phase difference to see destructive interference. Because if you just say multiple of 180, 360 is also a multiple of 180, and that is constructive interference. So you need to say odd multiple, which actually then tells us that, which makes sure that trough of one falls on the crust of the other. Does that make sense? I hope it does. Now, the other thing we have about waves is uh, whether they are coherent or not. So two sources are coherent if they have the same wavelength and frequency and a fixed phase difference. They would have a fixed phase difference anyway if they have the same wavelength and frequency. So the two waves are said to be coherent if basically they are identical. First of all, they have the same wavelength and frequency, and they have a fixed phase difference. So they would always have a fixed phase difference if they have the same wavelength anyway, which means that any point, like the other wave is traveling like this. At any point, if you try to measure the phase difference, like this crust to this crust, or maybe this crust to this crust, it will always stay the same. It's not like one wave is traveling quicker than the other because they have the same wavelength. All right. So for two sources to be coherent, same wave, it should have the same wavelength and frequency, and the phase difference should be fixed, which should be fixed if both of them have the same wavelength. All right. So you should remember coherent light sources, which just means they have the same uh, wavelength, same frequency, and same fixed phase difference everywhere. Now, going a bit deeper in interference. Now, when is there a constructive interference or destructive interference? As I said, in terms of the phase difference needs to be uh, multiple of 2 pi or 360 degrees to have constructive interference, because that makes sure that crust of one falls on the crust of the other. And for the destructive interference, it should be an odd multiple of 180 degrees or pi to make sure that crust of one falls on the trough of the other. There's another thing that we can measure. So that was in angles that we measured. That was the phase difference or phase. We can measure the path difference. The path difference would be if, I don't know why they have not shown any example here, but the path difference would be if you have another wave, how much distance it has from the other. Like crust of one has the distance from crust of the other. Obviously, if they are in phase to each other, which means crust falls on the crust, there would be a zero path length between them because there's no difference between them. But if crust falls on trough of the other, and you measure the distance from the crust of this to the adjacent crust of the other one, that would come out to be half of the wavelength. So sorry, yes, half of the wavelength. So if you can measure it in path difference, you can measure it in phase difference. Both of them can tell you if it's going to be a constructive or destructive interference. I'm just going to read this so that we don't miss anything. Whether you get constructive or destructive interference at a point depends on how much further one wave has traveled than the other wave to get to that point. So yeah, so how much further one has traveled to the other to get to that point, because you will see it in double slit experiment as well, how we find the fringes. So obviously, if it has traveled half of wavelength more than the other, then crust would fall on trough of the other wave, and they would be destructive interference in that case. So you can explain constructive and destructive interference using phase difference as well as the path difference. You should do it in both ways. The amount by which the wave path traveled by one wave is longer than the path traveled by the other wave is called the path difference. So you measure it in terms of wavelength. Both of them are coherent light sources, because in your course we are going to just study constructive and destructive interference, knowing that the two sources are coherent to each other, which means they have the same wavelength and frequency and fixed path difference. So the amount by which the path traveled by one wave is longer than the path traveled by the other wave is called path difference. It could be lambda by 2, that the other wave has traveled more, which would mean it's destructive interference, because uh, there would be a difference of path, there would be a difference of phase equal to 180 degrees in that case as well. At any point, an equal distance from both sources, you will get constructive interference. You can also get constructive interference at any point where the path difference is a whole. So constructive interference can happen when the path difference is zero, when they are both traveling like this, or when one starts away from the other. Still, if the crust of that falls on the crust of the other, it has, which means that it has a path difference of maybe one lambda or two lambda or three lambda. It will still be a constructive interference. At any point an equal distance from both sources, you will get constructive interference. You also get constructive interference at any point where the path difference is a whole number of wavelengths, at point where the path difference is an odd number of half wavelengths. Similar to phase difference, you have to take the multiple of half wavelength with an odd number, so that you don't end up with a full wavelength in any way. The waves arrive out of phase, which means they are at 180 degrees to each other, or an odd multiple of 180 degrees, and you get destructive interference. So for constructive interference in terms of path difference, the path difference should be n lambda, where n is an integer, so it can be have a zero value as well. So it could be zero, or it could be lambda, one lambda, two, three, four, five. Destructive interference is an odd multiple of the wavelength, so that crust falls on the trough of the other. So 2n plus 1 over 2 gives us an odd number. Whatever value of integer you give to n, you'll get an odd number. So it just ensures that you get an odd multiple of lambda in that case. I hope it makes sense. Okay, all right. Uh, Sorry. Mm, it gets an half wavelength. Like it can be one and a half, two and a half, or half. So the wavelength difference should be half, odd multiple of half wavelength in that case. All right. So yeah, we'll just go through double slit experiment. It will make more sense now. Okay. Demonstrating two source interference for EM radiation is harder. Okay, fine. Let's just go through the double slit experiment directly. So laser light is coherent because it is coming from the same source. It's just split because of two slits that are there. So we already know they should be coherent because same source is generating them. Same, so they would have same wavelength, same frequency, same path difference, because they are just traveling straight till up till this point. They're just traveling straight. So laser light is coherent and monochromatic. Monochromatic just means that they don't have more than one wavelength. It's just a single wavelength of light source that is there. Maybe it's a red laser, so it just has one wavelength associated with the uh, red light. The slits have to be about this, as I said, for diffraction, they have to be comparable to the size of the wavelength. So they are saying the same thing. The slits have to be about the same size as the wavelength of the laser light so that it is diffracted. Then the light from the slits acts like two coherent point sources. So it just behaves, in this case it just behaves like that it's just two sources and not one, because you have two slits, so it just seems like that they are two sources. You get a pattern of light and dark fringes depending on whether constructive or destructive interference is taking place. Now you have a screen here, and as I think you would already know that in center you have the brightest spot, then you have a dark spot, then you have a bright spot again. So this only means that the path difference in the center was a multiple of lambda, or just equal to zero. And at the dark spot, it just means that the path difference is an odd multiple of half wavelength. And again, the bright spot just means that path difference is equal to n lambda. So, and you can also explain it in terms of phase difference as well. But they usually like it to be explained in terms of path difference. So we're just gonna stick to that. So you can see that the center one, the path difference is zero because both of them have traveled the same distance. They're coming from the same source, traveled the same distance. This dark spot, obviously, this would have traveled like this at an angle, and this would have traveled at a shorter angle. So it has covered less distance than this one. And if it's a dark spot, then this would definitely be a difference of lambda by 2 in this case, because that's the first dark spot, it would be lambda by 2. Then this one would have, so it's a bright spot, it would have a part difference of because this had 0, this should have a part difference of lambda. Then again the dark spot should have an odd multiple of lambda by 2. So you can judge what it should be, so it's 3 times lambda by 2. So that is how you see constructive and destructive interference following these equations. So that is why you see this kind of pattern on the screen when you perform the double slit experiment. I hope this makes sense. Again, coming to some formulas, you can quantify what you saw in the double slit experiment. So basically, you can find the fringe spacing, which is the spacing between these uh, dark and bright spots. So the fringe spacing x, wavelength lambda, spacing between slits is denoted by a. So whatever is the distance between these two slits, denoted by a, and the distance from slits to the screen. So this distance is d. uh, are all related. So this is the formula that you just need to remember. We don't need to derive this. So fringe spacing is x equals lambda d over a. So that is what it is. So x basically tells us the spacing between the fringes. Uh, since the wave, okay, the fringe spacing is big enough. Okay, so you can always find lambda using this. What wavelength of light source you used, looking at the fringe spacing and knowing the distance between the slits and the screen, and also knowing the distance between the slits as well. So this is the formula that you just need to remember. All right. So this was double slit experiment. You can use a diffraction grating. What is a diffraction grating? It is similar to what slits are, but it just has multiple slits instead of just two slits. So that is called a diffraction grating. So if you have any diffraction grating in the lab, it would tell you how many of spacings are there in per meter or maybe some unit. So you know what the distance between them is. So you know the distance between the slits, which is a in this case. So you can measure the wavelength of light again. So this was the formula that was associated with double slit experiment when you had the double slits. Now they are again going to use another formula to measure the wavelength using a diffraction grating. Now in this you use again a monochromatic light, the lines of maximum brightness at the center called so now we call where the light is maximum in the center, we call it zero order. Then we have the first order, where the second point on both the sides where you have bright fringe. Then third order, sorry, second order where the third bright fringe is, and the fourth order where the fourth one is. So third order where the fourth one is, yes. So uh, you can use basic trigonometry to find that. So this is x. X is the fringe spacing as we saw above. So this is x, this is theta, what it makes with the center bright fringe, uh, and d is the distance. So all of the all of them are denoted by the same like same units, same symbols actually. So you can use basic trigonometry like they have used, that tan theta in this case would be equal to x over d, right? And if the angle is so small, you can basically take like the approximation that tan theta is almost equal to theta, and then you will get the equation theta is equal to x over d. So you can maybe use this, not this equation, but when we come to this equation, this is one that you can use. So if you know the slit separation d, whatever is the separation in the slits, what order what so whenever you have a grating, you'll use this formula. If you know the slit separation d, what order maximum you are observing n, so you should know the order as well, which one you are observing. Center is 0, then you have n1, n2, and n3. uh, and angle between the maximum and the incident light theta, you can find the wavelength of incident light. So you can basically, you don't need to know how they have derived it, just need to know. So that is not part of the course, so you just need to know the formula and have the basic understanding of it. So d is the distance, this is the distance of the slits in the grating, the small d. Sine theta is the angle theta that it makes with that first order from the center to the that whatever order you are choosing, because n will describe what order that is there. uh, Okay, and lambda is the way. So you can basically, if you know everything here, you can find lambda from this equation as well. I hope it makes sense. So yeah, a lot of formulas I would say we have gone through, but most of them are related to diffraction. You should know that when it's grating, you have to use this formula, I think, and for the double slit, you have to use this formula. So that is the only difference that is there. Um, if okay, this capital N actually represents uh, how many slits are there. So you can, if you have like a, then the slit separation d, if the slit separation is d, uh, so sorry, if the grating has n slits per meter, so there are n number of slits per meter. So n is basically tells you how many slits are there per meter in that grating. Then the slit separation, which is d, you can basically get like the distance between the two. So that is what it is. All right. So you can draw a general conclusion from this. I will just go through that so we know that you guys understand it. So d sine theta equals n lambda. If lambda is bigger, if you have a bigger wavelength of light, sine theta is going to be big because you can see a direct relation between them. This means that the larger the wavelength, the more the pattern will spread out. You will see on the screen that the first order, second order are further like apart from the zeroth order. So it depends on the wavelength. If d is bigger, which is the spacing between the slits, sine theta is smaller because they have an inverse relation. This means that the coarser the grating, the less the pattern will spread out. Values of sine theta greater than 1 are impossible. So because it's sine theta, you can never have sine theta equal to something greater than 1. So if a certain n you get a result of more than 1 for sine theta, you know that that order does not exist. So obviously there must be a limit to where it spreads, right? It can't be like it has an infinite number of orders. So there is some split, and obviously after the light has passed through that so through those gratings, obviously they're not going to spread like more, they're just going to go in that angle. So you can see the same thing using white light as well. So if, because at this point we just saw monochromatic light, it had only same one wavelength. White light has multiple wavelengths, as you know, it comprises of all of those 7 colors together. So it's a mixture of colors. So if you diffract that, you will see patterns like these, so on the screen. So you can see now, the thing that you need to know is you can see that this violet color that is closer, that has less angle made from the zeroth order. And if you think about it, violet color has the shortest wavelength in the visible light. So if lambda is smaller, theta is smaller because they are directly related to each other. If lambda is greater in case of red light, theta would be greater as well, and that's why we see red at the far side and violet is closer to the zeroth order, if that makes sense. All right. Astronomers and chemists often need to study spectra to help identify elements. They use diffraction gratings rather than prisms because they're more accurate. Okay. All right. Never mind. I think we are almost uh, to the close. So, stationary waves, when a progressive wave is reflected at a boundary. So stationary waves are formed when there is a reflection of the waves and then they interfere. So interference is part of stationary waves as well. There is some interference, and that's why we see a stationary wave. A stationary wave is the superposition of two progressive waves. So one incident, the other one is the one that is being reflected back. So they actually interfere with each other. They are traveling in the opposite direction, and there's some superposition happening. When superposition happens, there is interference that is happening. So this phenomena that makes it using those two is basically stationary waves. So you get stationary waves when a progressive wave is reflected at a boundary. A stationary wave is the superposition of two progressive waves with the same wavelength. Up till now, we have only discussed coherent waves, so we already know that they should have same wavelength moving in opposite direction. Unlike progressive waves, no energy is transmitted by a stationary wave because everything that is going in this direction is coming back as well. So the net transfer of energy is just zero. You can demonstrate stationary wave by attaching a vibration transducer at one end of a stretched string. Okay, not that important. For most frequencies, the resultant pattern is a jumble. However, if you alter the signal generator so the transducer produces an exact number of waves, you basically need to play with your signal generator to be able to visualize it. Obviously, there would be whatever frequency you are giving using the signal generator, there would be some stationary waves, but you may not be able to like identify them. So you have to play with the frequency of the signal generator to be able to visualize it better. That is what it says. At these resonant frequencies, you get stationary waves where the pattern does not move. It looks like it's not moving. So wherever there is amplitude, it just keeps on doing that. And wherever there is wherever there is amplitude, like where there is the maximum distance, we call that point as antinode. And wherever there is you see that nothing is getting disturbed, it just stays at the same point, that is called a node. So at these resonant frequencies you get a stationary wave where the pattern does not move. It looks like it's not moving, it just stays like that because it's not traveling anywhere. The amplitude is just at this point. This point will always be the node which is not moving. So that is what it is. Now coming to some specifics of it, each particle vibrates at right angle to the string. Nodes are where the amplitude of the vibration is zero. So nodes are the point where the amplitude is zero. We already know antinodes are the point where there is a maximum amplitude. At resonant frequencies, an exact number of half wavelength. Okay, so okay, at resonant frequencies, an exact number of half wavelengths fit into the string. So if you see this example, this is a half wavelength that goes through it. So this we would say is the resonance frequency that you have provided with the signal generator. Now we'll discuss what are the fundamental modes of. So the standing wave above is vibrating at the lowest possible resonant frequency because if you reduce the frequency at that point, you won't see any stationary wave. And at the fundamental mode of vibration, uh, you basically just have two nodes and one antinode, which means just half of the wavelength you can see. So that is called the fundamental mode of vibration, also called the first harmonic. You should know that it has one loop with a node at each end. So this is fundamental mode of vibration. It has the fundamental frequency associated to it. It is half of the wavelength. It has one antinode and two nodes. If you go beyond that to the second harmonic, so this was the first harmonic. Second harmonic just means that you will have two loops, which means three nodes and two antinodes. And if you keep on going like that, so the third harmonic will have three loops. So one, two, three, four nodes and three antinodes. That makes sense. All right. So first harmonic, just half the wavelength. Second harmonic, distance is one wavelength. Like the total of this is one wavelength. Third harmonic, it's one and a half wavelength. All right. So this is important. You should remember fundamental mode of vibration, fundamental frequency, first harmonic. You should know how many, the distance is equal to how many of wavelength. You should know because the questions will come related to this. And then discussing these longitudinal stationary waves, these are also important. So these are some musical instruments. There obviously there's some frequencies which will resonate and stationary wave will be set up. If the instrument has a closed end like this one, a node will form there. So you should know for the fundamental frequency, which is the smallest frequency you give to it, you get the lowest resonant frequency when the length L of the pipe is quarter a wavelength. So whenever you have like a fundamental frequency through like a musical instrument, and one end is closed, other is open because you have to give it the sound wave. At the fundamental frequency, the distance would be equal to lambda over 4. All right. And if the end is opened at the fundamental frequency or the shortest frequency you can give to it, you will have total, the length would be equal to total of lambda by 2. So this is what you need to remember. You should know that this would be an NT node at the for the fundamental frequency with a closed end, and there will be a node at the end which is closed. For the end that is opened, for when the other end is opened as well, you will have the fundamental frequency creating a wavelength which is the length would be equal to lambda by 2, and the other end would also have an NT node, just like this when one of the end was open, so you had NT node there. So that is what you need to know as well. Yeah, so this would be equal to a half wavelength. So a question can come that is, they give you the length and they say calculate the wavelength. So you should remember that when it is closed, what is the length in terms of the wavelength? When it is open, what is the length in terms of the wavelength? So there in this example, they just have the tuning fork, and for the tuning fork, we know what the frequency is. So what they do is they keep, so obviously this is a closed end, so they keep on coming down until they hear a loud sound. So the shortest distance where they hear a loud sound actually tells us that it should be at the fundamental frequency at the what's that called, at the first harmonic. So in that case, so basically this distance should be equal to lambda 4 at that point. So you have to come down as much as possible to find this point, and you know that total length would be equal to lambda by 4, and that's how you can find what was the wavelength associated with that sound that was being produced by the tuning fork. That makes sense. The vibration produced by that. Once you know the frequency and wavelength of stationary sound wave, you can work out the speed of sound using the equation V equals F lambda. I hope that this is clear. So you just need to remember these things. First harmonic, half wavelength. Second harmonic, uh, you have like a you have like a full wavelength. Third harmonic, you have 1.5 wavelength. For musical instruments, one end is closed. Uh, you will have the frequency where it resonates. Smallest length where it resonates would be lambda by 4. If it is open, it would be lambda by 2. All right. Yeah, so that was all of the theory that was around waves. Now let's quickly just maybe solve uh, maybe one question from somewhere so that we have the understanding of that. So let's see. So two progressive waves A and B meet at a point P. So they meet at a point P. So this is a point P that is being described in this graph because this is displacement versus time graph. So this is, they have taken just a single point and they see what happens to the waves at that point. The displacement x against time graph for A and B at that point are shown below. Explain how the graph shows the waves are coherent. So if you remember the conditions for coherent waves, they should have the same wavelength, they should have the same frequency. We can't measure the frequency from this directly, right? And the path difference should be or phase difference should be constant. So if you see, the path difference never changes from here to here, it's the same distance. that is from this crust to this crust. So the path difference is not changing. I think that should be uh, from the graph, you can basically tell it in this way, or you can measure the wavelength as well. But I think the path difference or the phase difference is constant would be should be your first answer. So let me just confirm it quickly. uh, Constant phase difference. So that should be your first answer from here. Just by looking at it, you can see it's always one block, big block away, the crust. And here you can also see it, it stays one big block away. So you'll just say that the phase difference is constant. So that's why we know it's coherent. You can also measure the wavelength, but it's a one marker question. So I think that should be more than enough. So now they say determine the frequency. Now they say determine the frequency f of the wave A. So this is a displacement versus time graph. As I told you guys that you can directly measure period from displacement versus time graph. So we can measure the period for wave A. So this one is wave A. So period would be, if I start from here, I would need to reach the same point again. And this is 4 seconds. So the period is 4 seconds for this one. So if I have measured it correctly, so sorry, it's milliseconds. So you need to convert it into seconds. And we know that frequency is just the inverse of period. So it would be 1 over 4 times 10 to the power minus 3, because the answer we need to give it in hertz. I don't have a calculator with me currently, so if you guys can not calculate it, I we can just see if yeah, so 4, so it's 0.004. The frequency comes out to be 0.004. So basically they have done the same thing here. They've just taken the inverse of period, got the period from the graph, and then it just tells you what the frequency is, right? Does it make sense to you guys? There's something that you still don't understand about the theory. If there are any questions, just let me know. Now, coming to the intensity, what do we remember about the intensity? We know that it's power over area, what the formula is. And the other thing we know is that its intensity is directly proportional to the amplitude squared. So from the graph, what we can get is just the amplitude. So let's see what the question is. The intensity of wave A is I naught. Determine the intensity of wave B in terms of I naught. So we know that the intensity of wave A is I naught. And we also know that it should be directly proportional to amplitude squared for I naught. So it's wave A. So what's the amplitude of wave A? It's 10 micrometer, right? Yeah, 10 micrometer. So it should be directly proportional to 10 times 10 to the power. It's micrometer, so I think it's 10 to the power minus 6. It should be squared. And intensity of wave B, let's say it's I, should also be directly proportional to its amplitude, which is uh, so one small box represents two in that case. So it's 24, right? So 24 micrometer. So 24 times 10 to the power minus 6 squared. Now, um, as told you, to change this into uh, an equation, we don't have the constant, but we know both of them would be equal to the same constant. So what we can do is we can just calculate the ratio. So let's say we can calculate I over I naught should be equal to 24 times 10 to the power minus 6 squared over uh, 10 times 10 to the power minus 6 squared. What you need to do is take I naught on the other side. So if I just do it in this part, it would be something like this. So you calculate this, then just times it by I naught. and you will get whatever the value you get from here would be it would basically times I naught would be the value. So I unfortunately I don't have a calculator right now, so I'm just gonna see if that is the correct way to do it. So 24 over 10. So it's all right. 10 to the power minus 6 would be cancelled out anyway. So we have done it correctly. That's fine. Determine the resultant displacement at the point P at time t equals 2.5 millisecond. Determine the resultant displacement at point P at 2.5 milliseconds. So 2.5 millisecond. Um, so one box is representing 1 millisecond. So 2 and 2.5 would be somewhere here. So that means this point for this one, and I go like this one, this point. So the value at this point is, so one small box is representing 2, so 6, 8, and 9. So this seems to be minus 9, and this one is, sorry, not 9, it's 7. Yeah, 7. This is minus 7, and this one is, uh, so this is 18, so this must be 17. So you need to, as I said, that these are basically vectors, and this because this is displacement. So you just add them up with the sign. So 17 minus 7 would give you 10. So the resultant displacement would be 10 micrometer because the unit here is micrometer. Let's see if I've done it correctly or I've, yeah. So that is 10 micrometer. So is there anything you guys don't understand so far in the theory or something? I think we're just going to conclude it here because I spend a lot of time on the theory. So I don't think we have time to do any more. Is there any questions?
Um, I got one.
Yeah, yeah,
So, first and foremost, thank you for the opportunity, and I've really enjoyed it. So,
yeah.
I was kind of just wondering if you have any more plans for other topics.
Maybe in the future, not right now, but what I have is, I think most of you guys are from year 12, right? So you must have like predicted exams or mocks coming up. Maybe some of you guys would have it in May or June. So what I have is, so I know that all of, so mostly you cover the AS course in which comes in your predicted which also gives you your predicted grades as well. So what I have is like a a quick like a program to cover all the course that comes in those exams, because I know that predicted grades are very important. So I have done it in the past. So to cover it in like, not to like go very quickly through the all of the topics, and cover it in a way that you guys are familiar with everything and you can solve any question that comes from that topic in the papers. Obviously I know that what kind of questions can be in the exams. So we basically cover all of the topics that would be, or maybe more, in 6 to 8 weeks. So we cover everything that you guys are going to be uh, examined on. So that is one of the programs that I run, and I think the new program would be starting from, I think it's 10th of April. So if I'll send you the details in at LinkedIn. So if you guys are interested, you can just let me know. But other like those free masterclass, maybe one I'll do on quantum physics maybe next month. So if you guys are interested in that, I'll just post it on LinkedIn so you can just contact me there. Is there any other question related to the topic that we covered from anyone? I would have gone through more questions, but I think we don't have enough time. But if you understand all of the, what I would say is, if you understand everything now and you understand like how to apply those formulas, I would recommend you to just go through the past papers, find the questions that are related to waves, and just solve all of them. So you don't have a lot of exams that you need to go through. It's from, I think it's from 2016 to 2023 that are on physics and math tutor. So you can just go through all the waves questions and just check your answers from the like the mark scheme. So I think that is the best way to move forward for you guys, just to make sure that what you have learned, you now know how to apply it. So are there any other questions related to the topic? If they are not, I'm just gonna end this call. Okay, thank you so much. Maybe I'll see you next time. Bye, guys.